This problem, which is 1-25 of our book, seems to be a long problem, but it's not difficult at all. All we need to do is understand what is going on. It says that a common procedure for measuring the velocity of an air stream. So over here we would be involved in the business of measuring the velocity of air. It involves the insertion of an electrically heated wire called a hot wire anemometer. And as many of you would know, that the device which is used to measure the velocity of air is called an anemometer. There are various types of anemometer. So a common procedure for measuring the velocity of an air stream involves the insertion of an electrically heated wire. So this is the wire that we see over here into the airflow with the axis of the wire oriented perpendicular to the flow direction. So the air would be flowing perpendicularly over the wire. So if this is the wire, so this would be the direction of the flow of air. The electrical energy dissipated in the wire is assumed to be transferred to the air by forced convection. So what would happen is that the electrical energy will flow through the wire. The heat would be dissipated and air will take it away. Air will in fact convect it away. So the air is flowing over the wire, which would make it the case of convection. The electrical energy dissipated in the wire is assumed to be transferred to the air via forced convection. So when the air will flow over that heated wire, it will take away that heat energy via convection. Hence, for a prescribed electrical power, the temperature of the wire would depend upon the convection coefficient. The temperature of the wire would depend upon the convection coefficient, because it would depend that how much energy is being convected away by air, which in turn would depend upon the velocity of the air. And if the air is moving with a smaller velocity, with lower velocity, then it will not be able to convect away large amounts of energy as heat. Whereas if the air is flowing with higher velocity, so then it would be able to convect away, it will be able to take away large amounts of energy as heat. By the way, all this phenomena will take place in that box which is called an anemometer. An anemometer is a device, and it just looks like a small box, and on that box we have, for example, a readout dial which gives us the value of the air velocity, but inside that box is all those things which happen in the hot wire anemometer. Now it says consider a wire of length L is equal to 20 millimeters. So this length of the wire, this complete length of the wire is in fact 20 millimeters and diameter 0.5 millimeters. So the diameter of this wire is 0.5 millimeters, for which a calibration of the form V is equal to 6.25 exponent minus 5 h square has been determined. So this is an expression using which the velocity will be calculated with the help of the value of h. This is the expression using which the air velocity would be calculated with the help of the value of the convection coefficient. So what will happen is that somehow that instrument will calculate h, and with the help of that value of h, it will have this equation embedded in it, and with the help of this equation the instrument will calculate the velocity and will give us the value on the dial on the screen. How this expression would have been developed, V is 6.25 exponent minus 5 h square. This is not the point of concern over here, but there are various techniques that can be used, such as regression, to develop such equations. And how the instrument will calculate h, I mean there is a very simple answer to it, that it would be using q is equal to h delta t. So it would be somehow measuring q, and area would be the area of this wire, n delta t, and with the help of q is equal to ha delta t, it will first calculate, the instrument will first calculate the value of the convection coefficient h, and then this equation would be programmed into it already, and with the help of this equation the instrument will calculate the value of the velocity of air, and it will show us the value of the velocity of air. Now the velocity v and the convection coefficient h have the units of meter per second and watts per meter square Kelvin respectively. Although this equation, which is v is 6.25 exponent minus 5 h square, does not seem balanced as far as the units are concerned. See, there may be a couple of reasons. 6.25 times exponent minus 5, there may be some constants in it. Number two, if this is an statistically developed equation using a tool such as regression, so those equations may not necessarily be dimensionally balanced all the time. So kindly do not get bothered with this fact that how can h square be reduced to velocity. Right, so those are of course q is equal to ha delta t would be dimensionally balanced, but those equations which are developed using some mathematical techniques or some statistical techniques may not be dimensionally balanced all the time. Okay, so in an application involving air at a temperature of 25 degrees Celsius, so air is flowing over this wire at a temperature of 25 degrees Celsius. The surface temperature of the anemometer is maintained at 75 degrees Celsius. So the TS of this wire, temperature of the surface of this wire, was found to be 75 degrees Celsius with a voltage drop of 5 volts and an electric current of 0.1 amperes. Of course, this is an electric wire, so therefore the electrical parameters are a voltage drop of 5 volts and an electric current when it draws an electric current of 0.1 amperes. So this is the data that we are given, and we are being asked to find out the velocity of the air that would be calculated by the instrument, by this anemometer, if all those parameters exist. So again the velocity will be found out using this expression 6.25 exponent minus 5 h square. But in order to use this equation, to calculate velocity, we must first calculate h, and h will be calculated using ha delta t, Newton's law of cooling. So if we start again with q is equal to ha delta t, where area would be 2 pi rl, because this is the area that will come into play if the air is flowing perpendicularly over the wire, and then we are given the length of the wire, we are given the diameter of the wire as 5 millimeters. The temperature of the surface of the wire is 75 Celsius, and T infinity, the temperature of air which is flowing over it, is at 25 degrees Celsius. Q would be calculated with the help of V into I. So there is a voltage drop of 5 volts and there is an electric current of drawn by this wire of 0.1 amperes. So 5 times 0.1 would be the Q. And if we calculate H using this expression, we get H as 318.3 watts per meter square Kelvin. We will then put this value of H in the expression, which is 6.25 exponent minus 5 h square, and we get the velocity as 6.3 meters per second. So the instrument will show us the velocity of 6.3 meters per second, but how does it calculate the velocity of air as 6.3 meters per second? This is calculated, or rather this is based upon heat transfer principles. Let's take one more problem, which is 1-28. It says that an overhead 25 meter long uninsulated industrial steam pipe of 100 millimeter diameter is routed through a building whose walls and air are at 25 degrees Celsius. So the length of the pipe is 25 meters and it is uninsulated. So a large amount of energy would be lost or wasted, right? And it is carrying steam. and then it says whose walls and air temperature are 25 degrees Celsius. See, you need to learn to read the problems out. If it says that the air temperature is this much, so it would be referring to convection. And if it says that the walls are at such and such temperature, then it would probably be referring to the phenomena of radiation. So those are all the hints towards the modes of heat transfer. Now it says that the pressurized steam maintains the pipe surface temperature of 150 degrees Celsius. So the surface temperature of the pipe is 150 degrees Celsius. Now that is another question, whether it is inside temperature or outside temperature, but we will see that whether we should take it as outside temperature or whether we should take it as inside temperature. And the coefficient associated with natural convection is 10 watts per meter square Kelvin. So when it says the coefficient associated with natural convection is 10, so the thing is that this would be the convection coefficient between the outer surface of the pipe and the surrounding air, because H cannot be this small if it is carrying steam. So since inside the pipe it is steam, so H would be a large quantity, relatively larger quantity. And when it says and the steam would be flowing with, of course, with a certain velocity, because the pipes carry water and steam with a substantial amount of velocity. So that would not be the case of, or may not be the case of, natural convection. But when it says the coefficient associated with natural convection, so consider your room in which you are sitting, or you are standing in an industrial facility, and there is a pipe, overhead pipe carrying steam. So where would natural convection take place? Of course it would take place on the outer surface of the pipe, where the air would be flowing over the outer surface of the pipe naturally, without any external aid, without any fan or a blower. The surface emissivity is 0.8, right? So as soon as you are told that the surface emissivity is 0.8, it means that you are now being asked to consider radiation heat transfer as well. Now it says that the surface emissivity, so we would take it as the emissivity of the outer surface of the pipe as 0.8. What is the rate of heat loss from the steam line? There are two parts. Let's start the first one first. So what is the total rate of heat loss from the steam line? So heat is being lost from the outer surface of the pipe via convection as well as via radiation. See, there are two hints. One is the temperature of the walls and the air, and then we are given the value of H, and we are given the value of emissivity as 0.8. So this is the first hint, and this is the second. It is not hint, rather it is been explicitly told. Since we are given the value of H and epsilon, it means that we need to consider convection and radiation both into account. So convection is HA delta T and radiation is sigma epsilon A, TS4 minus T surrounding 4. So area through which the convection heat transfer will take place would be the outer surface of the pipe, which is pi dl, and the same area would be the area through which the radiation heat transfer will take place. The convection heat transfer will take place between the outer surface of the pipe and the surrounding air, whereas the radiation heat transfer will take place between the outer surface of the pipe and the walls of that building. So H is 10, temperature of the surface of the pipe is 150. The air is flowing over the pipe at 25 degrees Celsius. The value of sigma is 5.65 exponent minus 8. Emissivity of the outer surface of the pipe is 0.8, and then the temperature of the surface of the pipe is 150 degrees Celsius, but And now we are bound to put the temperatures in Kelvin if we are using radiation. See, because in convection it is delta T, but in radiation it is not delta T. It is T14 minus T2 to the power 4. So delta T in Kelvin in Celsius is the same as the delta T in Kelvin, but the same is not true if it is not delta T. So the same principle cannot be applied in case of radiation. Therefore over here we are bound to put the temperatures in Kelvin. So 150 plus 273 will be 423, and then the surrounding air, which is at and the walls, you can well write over here the temperature of the walls, the value of which is 25. So 25 plus 273 will give us 298. So we will get the total heat loss as 18,413 watts. Kindly note that I was just mentioning that we are given that the pipe surface temperature is 150. So we have considered it to be the outer surface temperature of the pipe. But if you see the mode of heat transfer through the thickness of the pipe would be conduction, and the steam pipes are usually made of some grade of steel or some other similar material, means metal, and metal are good conductors. So there would be a small difference between the inner surface of the pipe and outer surface temperature of the pipe. There would be a small temperature difference. Why? Because if it is a metallic pipe, it would offer low resistance. So, and if the resistance is low, the temperature difference would not be that large. The temperature difference between the inner surface of the pipe and outer surface of the pipe would not be that large. So we will see in future that in some of the cases we would be assuming that the inner and outer surface temperature of the pipe are almost the same. It means that we are saying that the pipe is highly conductive in nature. The material of the pipe is highly conductive in nature. So over here, since we are considering the heat loss, and the heat will be lost from the outer surface of the pipe, so we will say that we are given the outer surface temperature of the pipe as 150 degrees Celsius. Now in part B, it says that if the steam is generated in a gas fired boiler, this steam which is being transferred is generated in a gas fired boiler, and that gas fired boiler is operating at an efficiency of 90%, right? And if the natural gas is priced at this much, then what is the cost of annual heat loss from the line? So this is the amount of heat which is being lost. So now we have to calculate its cost. So we need to find out the annual cost of heating. Now this 18413.748 watts are being lost from the pipe, and this is being generated in the gas fired boiler, which is operating at an efficiency of 90%. So we will divide it by 90%. So in fact 20,459 watts would come under consideration if the efficiency of the gas fired boiler had been 100%. So it would have remained 18413, but since now it is not operating at an efficiency of 100%, it is operating at an efficiency of 90%. So so the amount of heat which is being lost is in fact 20459 and not 18413. And you should also keep in mind those figures, that the boiler has an efficiency of 90%. So the boilers usually operate in the ranges of 75, 80, 85, 90% efficiency. Now if we may write this watt as joules per second. It means that 20,459 watts, 20,459 joules are being lost in 1 second, and we need to calculate the annual. We need to calculate the annual cost of heating. So if so many joules are being lost in 1 second, then the question would come into mind that how many joules are being lost in 1 year. So all we need to do is multiply this value of 20459 by the number of seconds in a year, which is 365 days times times 24 hours in a day, times times 60 minutes in 1 hour, times 60 seconds in 1 minute. So if you multiply this value by 365 days in a year times 24 hours in a day times 60 minutes in 1 hour times 60 seconds in 1 minute, so we get so many joules per year. So 6.4 exponent 11 joules would be lost in 1 year. And now since the cost of the gas is $0.02 per megajoule, so 1 megajoule costs $0.02, so therefore 1 joule will cost 0.02 divided by 1 mega. So 0.02 divided by 10 exponent 6. How many joules are being lost? 6.452. So we will multiply it on both sides of this equation. So if we multiply 0.02 divided by 1 million by 6.452 exponent 11, we get 12904 dollars. So this is the heat loss. This is the cost of the heat loss on an annual basis. Now if we insulate the pipe, we would be able to reduce it drastically, and that is why the steam pipes or any heated pipes are insulated. In fact, they serve two purposes. They not only reduce the amount of heat loss, thus reducing the cost of heat loss, they also provide an accident free environment, because if there is a pipe which is at a very high temperature and if someone, God forbid, touches it, of course it would be a severe accident, it may be fatal even. So however, if it is insulated, if it is covered with an insulation, so if someone touches it accidentally, so it would not harm the worker over there. Now let's take the last problem before we end the problems of chapter number 1. It's 129, and it is an interesting problem as well. It says that under conditions for which the same room temperature is maintained by a heating or a cooling system, under conditions for which the same room temperature is maintained by heating or cooling conditions. So if it is winter time, we would be heating the room so as to maintain the room temperature, and if it is summer time, then we would be cooling the system to maintain the room temperature. So if we are maintaining the room temperature, it is not uncommon for a person to feel chilled in winter but comfortable in summer. So what this problem is saying is that if it is winter time and if we turn the heater on, then maintaining the air through heater will make the person feel chilled. But if the same room air temperature is being maintained in summer season by cooling, then the person will not feel that chilled. So we are being asked to provide a plausible explanation for this situation, of course with calculations, by considering a room. So now we are considering a room whose air temperature is maintained at 20 degrees Celsius throughout the year. So if it is summertime, it will be maintained around 20 degrees Celsius by cooling, and if it is winter time, then it will be maintained around this value of 20 degrees Celsius by heating. While the walls of the room are nominally at 27 degrees Celsius and 14 degrees Celsius in summer and winter respectively. See, it says while the walls of the room. So you should start thinking about the radiation heat transfer. It says while the walls of the room are nominally at 27 degrees Celsius in summer. Of course, the walls are at a higher temperature in summer and the walls are at a lower temperature in winter. The exposed surface of a person in the room may be assumed to be at a temperature of 32 degrees Celsius throughout the year, which is the normal temperature of a human body, and to have an emissivity of 0.9. So we are given the emissivity of the human body. So as soon as we are given the emissivity, so we are being told that radiation heat transfer will come into play. And it then says the coefficient associated with the heat transfer by natural convection between the person and the surrounding air is 2 watts per square meter Kelvin or degree Celsius. So we are given the value of H between the person's body and the surrounding air as 2 watts per meter square Kelvin. So this is where the convection will take place, and there would be radiation between the person's body and the walls of the room, which are at 27 degrees Celsius in summer and 14 degrees Celsius in winter. So we are being told that in fact the heat will be lost from the person's body via convection and as well as via radiation, right? So the total heat loss from that person's body would be via convection and radiation. Convection would be HA delta T and radiation would be sigma epsilon A T14 minus T24 or TS4 minus T surrounding 4. By all means you can put over here temperature of walls. So we are not given the area of that person's body, so we will take the area into the denominator of Q and we would be calculating the heat flux Q by A, watts per square meter. The right hand side is H times delta T plus sigma epsilon TS4 minus T walls 4. Now H is 2. TS, temperature of the surface of that person, is at 32 degrees Celsius. Temperature of the surrounding air is being maintained at 20 degrees Celsius throughout the year. Sigma is 5.67 exponent minus 8. Epsilon is 0.9. Temperature of the surface of the person's body is 32 plus 273, because now we are considering radiation, so we are bound to put the temperatures in Kelvin, minus the temperature of the wall in summer. If we are working the things out for summer, so in summer they are at 27 degrees Celsius. So 27 plus 273 will give us 300. So the heat loss is via convection is 24 and the heat loss via radiation is 28.2, the sum of which is 52.2. So this is the amount of heat which is being lost from that person body to the surrounding air and walls, which is 52 watts per square meter. And if we put the values corresponding to winter season, so in winter what is changing? See, H remains 2. The person's own body temperature remains 32. We are maintaining T infinity via heating in winter at 20 degrees Celsius. So all which is being changed is in fact the temperature of the walls of the room, and in winter the temperature of the walls of the room becomes 14 degrees Celsius. So 14 plus 273 will give us 287, and we get the heat loss via convection as 24 and heat loss via radiation as 95.3, thereby the sum being 119.3. See what is happening. Compare the two. if we compare summer and winter, the heat lost via convection remains the same. Why? Because we were able to maintain the temperature of the room and the convection heat loss remains the same. But what we were not able to control was the temperature of the walls, or is the temperature of the walls. So therefore what happens is that in winter, when the walls are at a lower temperature, at 14 degrees Celsius, this is not minus 14, this is plus 14 degrees Celsius. So since the walls go at a lower temperature in winter time, so therefore the temperature difference between the person's body and the wall becomes greater, and therefore the radiation heat transfer between the person's body and the walls would therefore increase from 28 to 95. So although we are maintaining the room air temperature via heating and cooling, but we are not maintaining the temperature of the walls of the room, and therefore the radiation heat transfer increases in winter, which results in an overall heat loss from that person's surface body, and therefore the person who was feeling very comfortable in summer feels chilled in winter time, because it is the radiation heat loss which is more for the reason that I have just explained.